All right, so chapter 13, properties of solutions. We've just finished up talking about metals. We've looked at liquids. Now we're going to look at solutions. So let me find my pen here. Where is my pen? There we go. All right, we'll make sure we're running good. There we go. Okay, so hopefully this is a nice break from some of the new material we've been learning, and we'll kind of harken back to your first year of chemistry. There will be some new things that we're going to talk about, like, well, we'll get to them when we get to them. I don't want to spoil the surprise, right? But hopefully most of this will be familiar. We'll say familiar, okay? So what is a solution? A solution is a homogeneous mixture of two or more pure substances. And we can think of this as uniform, all right? In the solution, the solute, like it says right there, is dispersed uniformly throughout the solvent. Okay, and there are two factors that are kind of at work that are going to determine if something can form a solution, and that is their natural tendency towards mixing and then the intermolecular forces between them. Now, what do we mean when we say natural tendency towards mixing? Well, if you're talking about a gas, then the mixing of a gas is going to be a spontaneous process. Okay, we know that gases act to fill whatever volume of container that they're put in. And the reason for that is that spreading out increases the entropy of that area. And we've studied entropy. We've looked at thermodynamics. We know that a spontaneous process should increase the entropy of the universe. And so when a gas spreads out, it does in fact increase that entropy. Now, just like we think about a gas, if you have a solution, a liquid solution that you are stirring up, right, mixing, if the entropy increase, or if we look at the entropy increase rather, that will favor the mixing of a solution. Now, something you have to overcome might be the intermolecular forces of attraction between solute particles, but something that can overcome that is the intermolecular forces of attraction between solute and solvent. So we've looked at IMFs, right? We've looked at dispersion forces and dipole-dipole forces and all that stuff. So now we want to apply that understanding from chapter 11 into the behavior of solute and solvent. So solute-solvent interactions have to, only occur when the components of a mixture are being mixed. So solvent-solute interactions only occur when you're mixing. Solute-solute interactions have to be overcome because you need to break apart the solute into discrete chunks in order to kind of hide it in your solution. Solvent-solvent interactions have to be overcome because you have to make room for the solute to fit in between those molecules. So there's kind of a dance that's going on there. Now, if we think back to first year chemistry, I know you've seen this picture before. I use it in my honors chemistry lectures. If you put sodium chloride into water and you want to dissolve it, then what you need to do is you need to hydrate your ions. You need to surround them in a hydration shell. In order to do that, you have to overcome the electrostatic force of attraction between Na and Cl minus. So we need to overcome that little bond right there, right, between the plus and the minus. We need to overcome it. And we also have the forces of attraction between water molecules, right? They're hydrogen bonds that are present. We need to space those out a little bit. So we need to push them apart. And when we do that, we end up with this space, all right? And in that space, we can put our chlorine ion or our sodium ion. So that's what we're talking about. There's this dance of overcoming certain attractive forces in order to have new forces come in. So there is still a force of attraction here, right, between the negative end of water and the positive end of this hydrated sodium ion, right? So we have forces in both directions. Now, we wouldn't be in AP chemistry if we didn't at least mention the fact that there is an enthalpy for mixing, just like there's an enthalpy for like everything else. And when we have a mixture occurring, the enthalpy of mixing needs to be close to the sum of the enthalpy of the solute and the enthalpy of the solvent. We can have exothermic mixtures. We can have endothermic mixtures. If you end up with a delta H of your solution, which is usually SOLN, and it is less than 0, we would say that it is exothermic, which we can see here on the left. And if you end up with a delta H of your solution that is greater than 0, then we are endothermic, which you can see on the right. So we have energy diagrams for mixing, just like we do for reactions. Now, speaking of reactions, it's important to point out that just because you mix two substances and one of them disappears, that doesn't mean that you have made a solution. Sometimes you have a reaction. A great example of that is nickel mixed with hydrochloric acid, which leaves you this very nice green hydrated compound there. So just because you're mixing two things, make sure that you know, am I making a reaction here or am I making a solution? Now, when you're making a solution, there is an opposing process. It's called crystallization. And if you mix solute and solvent, they have to kind of reach an equilibrium there between the crystallization of the solute coming out of the solution and the dissolving or the dissociation of your solute into the solution. When they are at equilibrium, then you have a saturated solution. Okay, if you're not at equilibrium yet, then you have an unsaturated solution. Now, solubility is the maximum amount of solute you can dissolve into a solvent at a given temperature. So that is the measure of that rate of, crystallization versus our solution making process, right? If you have a saturated solution, we've reached the solubility limit of that substance. If you have an unsaturated solution, you haven't reached the solubility limit. Now, this slideshow, I love it. It says, surprisingly, there's one more type of solution. I think we've been in chemistry long enough to know that it should probably say, unsurprisingly, there is a third, right? There's always an exception. And that is our supersaturated solution. Now, supersaturated solutions are uncommon to find in nature because this occurs when you have a solvent that holds more solute than is normally possible at whatever temperature and pressure that you're at. Now, these are going to be unstable. If you scratch the side of the glass, or if you drop a little tiny solid piece of whatever your solvent is in there, you can force this solution to crystallize, and it usually happens very rapidly. So these are pretty cool. Sodium acetate is a common supersaturated solution that we play with in the lab. It's one that as a liquid you can kind of pour out and it will solidify as you pour it. There's some pretty cool YouTube videos of that if you want to look those up. Now, in year one chem, we do talk about factors that affect solubility. We focus mainly on temperature, agitation, and our solute-solvent interactions. I'm going to introduce pressure because we do need to talk about solubility in terms of gases as well. But let's just review solute-solvent interactions first. So remember the little moniker, right? Like dissolves like. That doesn't explain everything, but it's a great place to start. When you're looking at like dissolves like, what you're talking about is if you have a really strong interaction between the solute and the solvent, there's going to be greater solubility of that solute in that solvent, okay? So if I have, say, we'll just use the old classic, right? NaCl and water, right? I'm going to get NaCl aqueous. So I can definitely dissolve those two things there. And it will be at equilibrium. When I'm thinking about that, well, I have an ion dipole interaction going on here, which is super strong. And so I would expect salt to be pretty soluble in water. All right, so that's the kind of like dissolves like examination that we're looking at there. Now, there are more molecules than just salt. We do need to think about, say, organic molecules, because organic molecules are really important to us as living things, right? And when we're looking at whether or not they will dissolve, we look for polarity. We know that, like dissolves like. So polar organic molecules are going to dissolve fairly well in water compared to non-polar organic molecules. Look for the potential for hydrogen bonding between your organic molecule and your water, right? So we know that water has this oxygen that is capable of engaging a hydrogen bond, right? And so if I have something like, just cyclohexane, well, yeah, I can go this O to that H, but this bond isn't very polar, and so that's going to be an uphill battle. On the other hand, if I have something like ethanol, which is down here, and I put my water molecule there, well, now I can definitely steal that, right? I can have some hydrogen bonding there, right, between the O and the H. There could be some O to the H on a water molecule bonding, right? Because this oxygen is going to have two lone pairs, so it can definitely form two hydrogen bonds. So when an organic molecule has oxygen presence that have lone pairs that's capable of hydrogen bonding, or if there's an F or if there's an N, right? Those are all good signs that an organic molecule will dissolve well in water. Now, when we're describing something's ability to dissolve, we use the word miscible. So if two liquids will mix together, and kind of the proportion of their mixing doesn't matter, we say that they are miscible. If they don't mix, we say they're immiscible. So hexane is a nonpolar compound. Water is polar, so they are immiscible in one another. Biological molecules like vitamin A and vitamin C are a common question that you may see in AP that asks you to kind of apply this stuff. So, why would you need to regularly eat vitamin C where you may not need to eat as much vitamin A? Oh, it's pretty simple. Vitamin A is fat soluble, so it will dissolve in your fat stores in your body if you eat too much of it. And then as you work through your fat stores, you will release that vitamin A at the same time. On the other hand, if you have a vitamin like vitamin C, any extra vitamin C you eat, you're just going to pee out, right? It's water soluble. So if your body doesn't use it, it's just going to flush it. Well, that means if let's say you eat an orange and then you get on a boat and you don't have any citrus for like 6 months, well, your body is going to be, experiencing a deficit of vitamin C, right? You might get scurvy. So that would be an example of how we could apply, which of these vitamins might we need. How can I look at those vitamins and know which one's fat soluble and which one's water soluble? Well, most of the molecule on vitamin A we can see is nonpolar. I know it's nonpolar because if I look at it, there's nothing but C and H, right? So we know that C and H forms a nonpolar bond. On the right end, it does have an OH group, a hydroxyl group. But that's the only group on it that is polar. So water could interact there, and that's about it. When I look at vitamin C, though, I see quite a few hydroxyl groups, and the more hydroxyl groups I see, also this oxygen right here, which can form hydrogen bonds with, a neighboring hydrogen, dash lines. It is very polar, right? Many polar groups are present on that molecule, so I'd expect it to dissolve in water. So I want to look for OH groups, maybe an N or an F. Now, those are things that we've talked about previously, right? We've looked at how liquids dissolve, how solids dissolve. Let's talk about gas for a minute, because solubility of solids and liquids is not affected by pressure, not appreciably, right? You would have to have it so much that it doesn't even it's not worth mentioning really. Gas solubility, on the other hand, is completely affected by pressure, even very low amounts of additional pressure. So we can definitely talk about pressure as it pertains to gas. Now, Henry's law is the law that we use to describe this, and it is the solubility of the gas is equal to the equilibrium K times the partial pressure of the gas above the solution. So we're looking at this. So this is the pressure of the gas, all right, and K is going to be this rate of up and down. We'll get more to K later. I know we've talked about it some, but it's an equilibrium component. It's really not a hard law to solve. It's just, whichever thing you're looking for, you divide out, right? So if you know K and you know SG, divide by K, you'll find the partial pressure of the gas. If you know K and PG, well, just multiply, you'll get the solubility of the gas, right? And, for the most part, when we're talking about Henry's law, I just want to point this out. We really do like these nice straight lines. Keep something in mind. Ideal gases are not real, right? But, they make good math sense. Anyway, temperature all right, when we talk about solids. As temperature increases, solubility increases, right? That's very true of 99% of solids. If we look at this graph over here, the only one that it's not true for is the cesium sulfate compound, which apparently as the temperature goes up, the solubility goes down. But in gases, as the temperature goes up, the solubility is going to decrease, all right? And this makes sense, right? In order to dissolve a gas into a liquid, you have to fit the gas molecules in between the liquid molecules. Gas molecules are energetic, right? They want to move around. As you increase the temperature of the liquid, those molecules have more kinetic energy. They get further apart, and so this creates holes, right? Like it's like a sieve. And those gas molecules, they just leave. They no longer dissolve. And so what we see as the temperature increases for a gas is that solubility trends downward. So that's very true. Now, where can we see this in real life? Well, I love to fly fish. Fly fishing is a tremendous amount of fun. I like to fly fish for trout. I know that if I want to catch trout, the best place to go is a cold river because cold rivers have higher oxygen contents than warm rivers. And trout are predators, right? They are predatory fish. They like to lay at the bottom in a cold pool, water moving past them, and they look up and they hunt, right? They wait for some unsuspecting prey to float by or fall into the river or whatever. Then they strike. If you look at warm water, I'm much less likely to find trout laying in warm water. So in the summertime, I'll go fishing over at like Goshen Pass. I'll fly fish in deeper pools, in the riffles, right, where the water is moving and it has some, is a little bit colder. I'm not going to really fly fish for trout anyway in that like slow moving stagnant water. I'm probably not going to catch a trout there because there's less oxygen. Now, we've talked about kind of some theory stuff, right? Let's switch gears just a bit. If you need to take a break, absolutely take a break. But let's talk about solution concentration as it as numbers are involved, right? So some quantitative solution concentration. And in order to do that, we need to talk about 6 things. Now, some of these you've seen before. Like I know you've seen molarity before. I know you've seen mole fractions before. But we're just going to hit all 6 real quick and make sure that we have them fresh in our mind. So what is a mass percentage? When you see the term percent, hopefully you think out of 100. So we take the ratio of the mass of our solute to the total solution mass, and we multiply it by 100. It's very similar to, say, the percent yield formula or the percent composition formula, right? It's the mass of the part divided by the mass of the whole times 100. So that's the mass percentage. So if you get one of those problems, there's the formula you're going to use. If we're calculating something in parts per million or parts per billion, which is pretty common for gases, especially, or if we're talking about like environmental chemistry, maybe how much pollutant is in a body of water, then we're still looking at mass of the solute to the total mass of the solution. But now, instead of multiplying by 100 to get a percent, we're going to multiply by times 10 to the 6 to get parts per million, or 10 to the 9th to get parts per billion. Technically, a percent is parts per 100, right? pph. So we multiply by 100. With parts per million or billion, we're just going to multiply by 10 to the 6th or 10 to the 9th, respectively. You're still doing mass of the part divided by the mass of the whole thing. People look at parts per million and they get really confused. Don't be confused by this. This is a simple calculation. Mass of the part divided by the mass of the whole times a million or times a billion. That's all that we're after. Now, the mole fraction, which we signify with this fancy X, is the ratio of moles of a substance to the total number of moles in a solution. So it's moles of the part divided by moles of the whole. Doesn't matter if you're looking at solute or solvent, you can still calculate the mole fraction. So part over whole, but now we're looking at moles instead of mass. Molarity, moles over liters, right, is something that we looked at last year when we talked about acids and bases. It's also something that we looked at this year in chapter 4. But molality is a little bit different. Molality is moles of solute per kilogram of solvent instead of liters. So this is a mass description, or this is a volume description. And very important, watch your penmanship. The only difference is R and L. The symbol for molarity is capital M. We use lowercase m for molality. Well, why do we need a mass versus volume description for concentration? Well, if water is your solvent, and water is the universal solvent, so it's highly likely that that will be the case, a diluted solution is going to be similar with molarity and molality at the same temperature. However, molarity is going to vary with temperature because the volume is going to change, right? If you heat up water, it expands. And if it expands, the volume is changing, right? If you cool down your water, it's going to contract. The volume is going to change, and that's going to change your molarity. On the other hand, mass doesn't change with temperature. So, I mean, if I have, 1 gram of oxygen and I heat it up, I still have 1 gram of oxygen, right? So molality is useful at various temperatures to describe concentration. Now, some of these calculations you're going to do are going to involve converting units. Remember, just use the factor label system. It's overviewed in Chapter 1 if you need to see it. And if you need to go from molality to molarity, use the density of the solution. All right, I made a special slide just for that so you would see it. So if you're going between molality and molarity, use the density of the solution. Now, another thing that we talk about with solutions is are the colligative properties that are associated with that solution, and they depend on the quantity of particles in a solution, not the identity of the particles. Okay, so it's just looking at how many things do you dissolve in the solvent, not necessarily what you dissolve in the solvent. And there are 4 main colligative properties we want to look at. We want to look at vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. I'm going to shy away from osmotic pressure just a little bit. I'm going to focus in on the other 3, but osmotic pressure, I mean, we'll mention it, just not in great detail. Now, vapor pressure is something we've already talked about this year. It is caused by, sorry, let me rewind that. As a review, it is the pressure of the gas above a solution, right? Pressing down the solution that is increased as some of those volatile solvent particles evaporate and go from the liquid to the gas phase. So there is solute-solvent intermolecular attraction. So when you put these little red spheres into our container, there are forces of attraction between the red and blue spheres, and they add an additional force that the vapor pressure would have to overcome for a molecule to go from the liquid phase to the gas phase. So as we add particles, as we add solute to our solvent, that is going to increase the amount of energy required to reach the gas phase. Thus, we will lower the vapor pressure in the solution compared to a pure solvent. So that's what's going on there. We have those additional forces of attraction. Now we measure this with Raoult's law, and we again assume ideal solutions just like we assume ideal gases. And Raoult's law tells us that the pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. Okay, and so obviously since this is a fraction, we would expect the P of the solution, right? The pressure of the solution. This is a fraction of the pure solvent. So it's going to be lower. All right, that's what we're going to find. Now, similarly speaking, boiling points are elevated when you want to, or when you start adding solutes. So they're going to be elevated though for the same reason. When you add your when you add your particles in there are more forces of attraction, which means, all right, you have lower vapor pressure. When the vapor pressure is lower, it takes a higher temperature for your vapor pressure to be equivalent to atmospheric pressure. Remember that the definition of the boiling point is the point where the vapor pressure equals atmospheric pressure. So if I'm lowering the vapor pressure of the solution from, we'll say, A to B, well, now in order to get the A and B to be equivalent, I have to go to the right on my temperature in order to go up, right, to find C. So when I lower the vapor pressure, I have to increase the temperature, and this will be a positive increased temperature. And so we're saying that we elevate our boiling point. The freezing point is depressed or lowered when you start adding solute. And when you look at that, it's because the triple point is going to adjust, all right, for your phase diagram. And so since it's going to go down, I now have to move to the left on my temperature scale, and that's going to lower my, what is the word here? Freezing point. Wow, sorry about that. Okay, we can calculate this using Van Hoff's factor. This was one of the questions, or this topic was one of the questions in the summer assignment. So I know this year, if you're watching this video after 2021-2020 school year, I know this year because of COVID-19, we did not have a required summer assignment, but I did put it out there for you to look at. So there is one of these problems in the summer assignment you can look at if you want to see an example of it. But basically, we use the TB of the solution minus the TB of the solvent to find IKBM in order to calculate the change in the boiling point or the change in the freezing point. If it's the freezing point, it's negative IKFM. Well, what is this Van Hoff factor? What is this I? Well, what it is it's taking into account how much dissociation is actually occurring in your molecules in the solution. Now, in theory, you take NaCl, right? You put it into a beaker of water, and you get Na, and you get Cl minus, right? We get a complete dissociation of two particles. Well, that's not actually what we find happens. We would expect to get 2, but at a 0.1 molar solution, we would get 1.87. 0.01 we get 1.94. 0.001 we get 1.97, right? We don't get quite 2. Some of them, that crystallization counter balance, some of them stay crystallized, and so we have to adjust for that. That's what Van Hoff factors do. Now, the last colligative property is osmotic pressure. Remember, osmosis is the movement of fluid across a semi-permeable membrane. The pressure that stops that is osmotic pressure. Now, osmotic pressure is another colligative property that involves a little I there, I times MRT, and we use capital pi in order to signify osmotic pressure. Now, if you have two solutions that are separated by a semi-permeable membrane and they have the same osmotic pressure, then there's no osmosis. If you have an isotonic solution, that's what you're talking about. And when we say no osmosis, keep in mind, so here's our semi-permeable membrane. That means the rate of A flowing to B is the same rate as B flowing to A. So it's no net movement. All right, that's what we're talking about there. If you have a hypotonic solution, then you must have lower osmotic pressure. And so the solvent is going to leave the solution faster than it's going to enter the solution. On the other hand, if you have a hypertonic solution, well, then your solvent is going to enter that at a higher rate than it's going to leave it with. So let's see, what does that look like in real life? Well, let's look at it in terms of biology. Let's look at blood cells. In an isotonic solution, the red blood cell is stable. Nothing is diffusing, or nothing is moving by osmosis through the membrane faster than it's moving out. So the red blood cell has no change. If you are in a hypertonic solution, you have what's called crenation. And crenation is when more of the fluid inside the red blood cell, more of that water is leaving than is coming in. And that's because there's a lot of solute outside. And so water wants to go outside of the cell in order to balance that out, to reach equilibrium. On the other hand, if you have a hypotonic solution, so this would be a hypotonic solution here, then you have very low solute in the blood. And so water from the blood is going into the cell to try to reach equilibrium, right? It wants the same ratio of solute to solvent in both places. Now, that can lead to hemolysis, which is when your red blood cells burst. This would be what would happen if you it's called your BCOP, your blood colloidal osmotic pressure. If your BCOP was to just go through the floor, right, and the number of dissolved solids in your blood was to drop, or if you were to drink, gallons of water and your blood was to become diluted, then this hypotonic scenario would be bad for you, right? Now, we've talked about colloidal properties. That's not something that you want to confuse with the word colloid, but we do need to talk about colloids to wrap up our discussion of solutions. So solutions are these homogeneous mixtures. Colloids are suspensions. They involve particles that are much bigger than individual ions or molecules, but they don't just float to the bottom because of gravity, right, or sink to the bottom because of gravity. So we call those colloids. A lot of them are gases dissolved into other gases, but sometimes we can get, more interesting things like marshmallows, which are solids dissolved into other solids, which are solids dissolved into gases, or rubies, which are solids dissolved into solids, right? So those are technically a colloid. Now, when we talk about colloids, hopefully in first year chemistry, you remember me talking about the Tyndall Effect, which is caused by the suspension of particles in the air and the fact that they can scatter rays of light. A solution will not do that. You can see that in this picture, this would be a solution because the light rays are just going straight through unscattered, but this must be a colloid because my light rays are all over the place, right? And we see them, and they're also not exiting, right? There's nothing coming out. So that's the Tyndall effect. It's why the sky is blue. It's why you see two different colors, like when a headlight's coming, if you're driving at night, right, and the headlights are coming around a turn, you see them coming through the air, right? There's that scattering effect that you can observe. Now, colloids and biomolecules are a pretty interesting, crossover between biology and chemistry. Some of these really large biomolecules are amphoteric, right? They have a hydrophilic end, they have hydrophobic ends, and these are pretty important because they can allow things that would otherwise not interact with an aqueous solution to interact. So ions can stick to the surface of these hydrophobic colloids, and then they can be turned into emulsification, or they can be turned into emulsions by emulsification. Now, stearate is a really important one of these in the human body. And what it does is it has this nonpolar end. So it kind of looks like a phospholipid. It has this nonpolar end, which can dissolve into these oil droplets, and it remains a little polar end sticking out. And so all these polar ends can now interact with water, and you can move a fat droplet in through your biological system. If we couldn't do that, we couldn't process fats. That would be a bad deal for the human body. Now, something else that's kind of interesting about this behavior is it does lead to this really nice circular fat droplet, right? Which, when you look at like milk through a microscope, you see all these circular droplets of fat suspended in water, and that's why. Now, something else you might notice when you look at a colloid is something called Brownian motion, and this is where I'm going to end the video. Brownian motion is pretty interesting. It's, if you have a window, right? That's a terrible window. There we go. And you're in a completely dark room, and, there's light shining in through the window. Okay, and you watch, you'll notice that there are these little particulates of dust. And some of them are going up, and some of them are going down, and some of them are moving, this way and that way and this way. And, they don't seem to have a pattern. Brownian motion explains the pattern. So what it is basically is when you have a large particle suspended in a fluid, in this case, a dust particle or a dust mote suspended in a gas, which is behaving as a fluid, the air, these little tiny molecules bump into the large particles, and they lead to random observed motion. The air molecules are way too small for us to see, but the dust particles are large enough to see. So we can directly observe the impact of all these millions of little tiny gas molecules hitting this larger particle. And that's called Brownian motion, after the scientist who discovered it. Trying to remember, I know his last name was Brown, obviously. I think he was studying pollen. I think he thought pollen was alive because it wiggled in the water. But what was actually happening was the water molecules were bumping into the pollen. So that's something that we see in colloidal environments. All right. So that kind of wraps up our chapter on solutions. Let me know if you have any questions, and I will be glad to give you guys a hand.